One of the most prominent themes of this channel is the discussion of possible futures and how we could feasibly attain those futures. I've talked about Dyson swarms, harvesting planets, and interstellar missions before on this channel, all possible visions of how our futures could look and operate. But what about afterwards? What kinds of things will humanity try to accomplish once all of our current day dreams have been perfected and become commonplace? What does our future's future look like? Welcome back to Serious Science, and this is what humanity will need to accomplish to become a K3 civilization. What do I mean by K3? Most of you may already know about the scale applied to prospected intelligent civilizations, based on the one universality we believe will be common among them all, no matter how alien they may act or think, by how much power their species will need to use to keep the lights on and the stellar reactors running. The Kardashev scale is usually divided into 3 sections, though higher ones have also been considered. A Type 1 or K1 civilization is thought to use all possible energy sources available to it on its homeworld, essentially mastering everything from nuclear reactions and wind energy to oceanic wave-based generators and thermoelectric plants sapping their world's molten cores. Humanity has obviously yet to reach this stage, and we currently fall as a K0.7 race. I would also like to mention before continuing that this scale measures power needs as opposed to technological advancement, as it mentions no necessity for certain methods of power generation or harvesting, only that the life qualified to place somewhere on the scale will need a certain amount of energy to sustain itself. This can be illustrated through imagining some kind of fungus that had grown to cover every available inch of land on its planet and used as many resources as it could to grow and survive. This kind of creature would essentially be a K1 species, despite having developed no technology or need for expansion other than what life already naturally dictates. K2 species are thought to require the amounts of energy only seen to be naturally produced by a star, having englobed their sun to absorb and transmit every photon of light into electricity. K3 civilizations would need the output of a galaxy's worth of stars to feed its population, requiring a now seriously impressive amount of technology to do so. They would be the kind of godlike alien races we sometimes see in fiction. They have captured billions of star systems and use each and every star to add to their power, causing their home galaxy to go dark in the night sky, becoming an infrared blob of invisible might. So how could we do it? Well, I want to begin theorizing about what we will need to accomplish this by stressing that this is entirely theoretical, as the difference between where we are now and this kind of civilization has often been described as the difference between us and amoebas. Humanity will be utterly unrecognizable to what it is today, having had many millions if not billions of years of evolution, genetic modification, and technological interweaving to become something vastly more advanced and powerful, if not a bit alien. I would also like to point out that as it stands today, humanity has only been around for about 200,000 years and has already changed substantially within that eye blink of cosmic time. Who knows what a billion years will do to what our descendants will think of as humanity. Now, what will it take to become those hyper beings we keep writing about? Well, if we are in a position to translate from a K2 to a K3, we will have already abandoned even the cleanest methods of power generation, such as nuclear and geothermal, and moved our solar panels directly around our own sun, harvesting all light it produces as well as possible other boons to power generation, such as magnetosphere manipulation and thermal couplings. Such a civilization would be primarily space-based, as trillions if not quadrillions of humans are expected to have been born and will all need space to live and grow. We will likely have extensive colonies on the planets we share the solar system with, and possibly a few colonies on interstellar worlds, but the bulk of humanity may either live aboard regulated and perfected orbital facilities or may exist as uploaded minds within powerful computer simulations. Our species will already look quite different to what it does now, even on this next highest tier, as such an encapsulation of an entire star, even if begun tomorrow, will take many thousands of years. During these years, we will probably have time to accomplish the kinds of far-out goals we discuss in fiction and reality, such as the curing of all diseases, both physical and mental, the reduction or elimination of aging, and maybe, just maybe, finally fusion. Interstellar missions will have been launched, the human brain will have been fully mapped and understood. New supermaterials and megastructures will have been launched, and all of our painful yet necessary destructions of our own planet will have been reversed, even the extinction of species both caused by us or by nature. Humanity at this stage will already resemble the kind of idealistic view we have today of what the best possible future would look like, even if the road to get there was a long and rocky one. But one day they will need more power to feed their engines of creation and their trillions of inhabitants. They will need to reach further out into the universe to find more, if they have not discovered some kind of easily manufacturable method of power generation that could compete with or even eclipse the outputs of stars. How do we make the next step? While I like to be optimistic about overcoming the speed limit of light through some uninvestigated trickery of the laws of physics, I do not know if such powerful ships will even exist in this far future, and we may just have to play by one or two of the universe's more dead-set rules. But this does not make our future's future ships any less impressive. Of course, models designed for monumental missions, such as colonization or megastructure construction, will be similarly monumental. I've often spoken about ships designed for such missions in past videos, one of which can be found here, and no matter how far technology may progress, even into the realms we think more of in the terms of magic today, to borrow a concept from Sagan, to make something big, you will need either something equally large or a large amount of collectible resources. This means that ships required to ferry billions or construct things such as orbital terraformation rings around prospect worlds will need to either be large enough to accomplish this from start to finish, or will need to gather the required materials upon arrival using an already necessitatively massive amount of processing and manufacturing forces, which can and will be continuously updated and miniaturized with many thousands of years of technological progress. These ships, as impressive as I hope I've made them out to be, will be the first of the initial stage of becoming a K3 civilization, as we will need to build places to stay as we harvest all the suns in the Milky Way to begin with. But of course, the ships carrying anything from small cargoes to terraformation rings may not be necessary, at least in their projected scale. In the far future, all the spaceship may be is an orbital tug, designed to get you through the real stellar engine. While we still do not know enough for me to comfortably speculate on faster-than-light travel methods, despite the best one we have envisioned so far requiring an even greater leap in theorization to even run, we still do not understand much about a similar topic, one that bends and merges space-time all the same. Wormhole travel is woefully misunderstood, as we still have no proof that it could even work, let alone be artificially constructed, but it is possible under previously reinforced math, especially the recent discovery of black holes. If space-time can be sufficiently affected through mass, rapid rotation, or another unforeseen method, we could theoretically generate two entangled wormholes, each leading to the other, though the use of the word entangled will most likely look and act nothing like what it means in particle physics today, more describing how connected these two distortions would be. One end of these wormholes could be moved, at sublight speed, to the orbit of a distant world or star, and act as an instantaneous gateway between the two, eliminating the need for spaceships with the exception of these foraging expeditions. Even this method of transportation may become tiring, and a new but similar method may be devised. If two dense and massive amounts of space-time warping matter in the shape of disks or rings were to be spun close to light speed in opposing directions, we may be able to not only bend the fabric of reality, but finally break it. If travel to what could be considered the outside face of the universe is proven possible, we may have just unlocked the ultimate in travel speed. It may be likely that such ships leaving the entirety of reality and all the laws that govern it will need to carry a bit of home with them in the shape of artificial bubbles of space-time, torn pieces of the universe we've left behind in order to keep everything contained within still existing. We've seen the fabric of reality bent and warped towards infinite points here in the modern-day universe, in the case of black holes, which we perhaps know a tiny amount more about than wormholes. If these seeming infinite collapse points are not simply bending reality far below its breaking point, but breaking it through their unimaginable forces, we could theoretically send objects through these tears in reality. Perhaps it would take an infinite amount of time to reach the other side, or fighting the amount of collapsing force a hole in the universe would feel with the gravitational attraction of literally the entire universe makes our tears last for mere femtoseconds is still a major unknown. Still, half the fun of the future is using what we know now to speculate on what could be a possibility, and if these factors do not hinder our exile from reality, there would be no such thing as distance, time, momentum, or any other governing law. We could theoretically manipulate this lawlessness into taking us anywhere no matter how far, both in distance and time, at no time at all. simply creating another of these distortions to re-enter creation. Though we may punch through our universe to discover something different entirely, a coexisting universe that formed alongside our own, one of an unknown number of others. Intra-universal travel, if the universes we are translating into resemble our own in any way that would keep our laws of physics from flying apart, may come about before we had even reached the boundaries of our own galaxy. If the outside of our universe proves too hostile or impassable as a method of movement, we could still use it to get around through the use of artificial constrictions of space-time. If we can essentially squeeze a specific section of space-time within extra-universal devices, we could section off small areas of incredibly gravitationally warped space-time, possibly allowing for near light speed and reactionless travel. Highways of tunneled space-time carrying all the major traffic of the human race as we start reaching the outer limits of our galaxy and turning the light of the stars into life-sustaining energy. There may be another thing we encounter as we colonize an entire galaxy. Not so much a threat as it will be an opportunity for unprecedented discovery and innovation. With just how many stars and planets there are in the wider universe, many of which resemble Earth in its inhabitability, we may soon discover the answer to one of the oldest questions we have ever asked. Are we alone? We may at one point in our expansion discover a planet that hosts life of its own. This life could take two routes, either remaining feral for as long as that life inhabits its planet, as we saw in the case of the dinosaurs before they're upset from the throne, or they could develop intelligence and begin calling out into the universe asking the same questions we have. If we discover alien life, feral or otherwise, we will be met with a difficult decision. These creatures will have just as much claim to their galaxy as we do to the same, and we may have to contend with sharing it. If those planets contain only feral life, I cannot imagine we would extinguish them by taking their star, perhaps leaving it untouched as a stellar preserve, maybe even watching to see if that life would eventually develop intelligence or simply enjoy life unaware. If we come across other intelligent races capable of comprehending the universe and their place within, we may not have found a hindrance or an unsuitable prospect, but an ally to help build and conquer and inhabit all of our shared galaxy with us. So far in our expansion efforts, we've started to weasel our way around spending thousands of years in transport, and have colonized millions of planets, star systems, and the nearby orbits of the stars within. Humanity will have changed in some unpredictable but advantageous manner, and we have more energy behind us than is modestly imaginable. We've only just begun the expansion outwards, as those millions of inhabited stars pale in comparison to the 100 billion we share a galaxy with. We may be able to speed up the process of arriving to them all, but the actual creation of everything needed to do so will take disgustingly long amounts of time to construct. Many tens of millions of years spent harvesting, terraforming, and constructing, even if done faster as we grew, will take many lifetimes of different stages, allowing for uncountable cultures to arise all across the galaxy. The amount of unimaginable change that humanity has already undergone simply moving from where we are today into the K2 stage will represent only a fraction of the time needed to reach and ensnare all the stars in our galaxy. As we progress through the growth stages on the road to becoming a K3 civilization, our race will change, expand, and progress millions of times over. Once we have finally reached the last star, we may think of our descendants as more alien than they are human. As we near the end of this mass colonization project, the only thing separating us from reaching this end stage will be time and heat constrictions. Heat is rarely discussed in surface-level discussions of future megastructure or mass colonization, but it is an insidious problem that has no apparent easy solution. Anything that moves or does work, from machines to flesh, produces waste heat. No matter how smart we can get with reusing and recycling the heat produced by our bodies and machines, there will always be a dangerous excess, one that must be released or redirected slowly due to the simple laws of physics that govern heat radiation. We can try to push as much heat as we can through a radiation system, but if we push it too far, we will melt that system. If humanity in this far future is creating worldwide colonies or gigantic and adaptive space cruisers, they will both need artificial radiation systems. This need for space-based systems can be easily seen even in a comparatively rudimentary manner aboard the International Space Station. All of the highlighted areas are where our human crews live and perform experiments. Everything else carries the systems needed to keep those tiny cylinders cool, powered, and pressurized. The white panels sticking out from the superstructure are what we use today to radiate heat. Heat is the enemy of everything we have ever made. Computers run slower as their components lose conductivity. Metals expand and crack, sensitive collectors and adhesives erode. There is no more certain a route our descendants will take than the reduction or elimination of this waste heat. In order for waste heat to be transferred, it must be done so into an area with a lower temperature, whether that be the water running through nuclear reactors or radiation panels on spacecraft. Heat is simply how quickly the atoms of a material vibrate and travel, as the more energy they move with, the more energy they will impart on whatever they strike in the form of heat. With our experiments in trying to reach absolute zero, we have come to the conclusion that such a temperature may never be reached, as there is a seemingly ever-present amount of atomic energy we cannot remove, keeping us from this temperature. Whether this is produced by the binding energies of atoms or through the dark energy contained by space-time itself is unknown, but our roadblock may be pointing us in another direction. If heat is simply the motion of atoms and particles over time, then time itself may become the best method of radiation we use in the far future. Time is not uniform and can bend and stretch as easily as space does. If we are able to either artificially generate these gravitational space-time warps or park closely around the orbits of a black hole, we may be able to dump our heat energy into them. As the atoms carrying this heat energy enter these warped sections of reality, they will experience no significant change, but will slow considerably to any outside observer, essentially cooling this matter through the stretching of time itself. Black hole radiators could become cornerstones of cities and ships that produce massive amounts of heat, dumping it entirely into one of nature's best erasers. If this can be achieved, the limit to how large we could build and how much work those machines could do would become infinite. So, as another recap before we reach the end of the stage, humanity is spread almost throughout the entire galaxy. Heat, time, gravity, and distance hold little to no resistance against us. We are functionally immortal and no longer resemble Homo sapiens, and our creations rival planets in their size and stars in their power. We are finally nearing the last outlier stars that orbit on the fringes of the Milky Way, almost closer to other galaxies than the center of our own, but still gravitationally bound to our home galaxy. What will we do with all this power once we have reached the final star? How distant are those last stars from our galaxy? The farthest currently discovered star that orbits the Milky Way is one about 900,000 light-years from Earth. To put that into perspective, our galaxy is only about 100,000 light-years across. Once we have arrived at this final outpost between us and intergalactic space, we will have finally become a K3 civilization, many millions if not billions of years after the first interstellar fleet had been launched. With the power of an entire galaxy under the hood, what would we do with all this energy? Well, the same thing we have always used energy for, making more humans, more cities, more vehicles, more advancements. But if we wanted to use a large portion of it all at once, we could start experimenting with truly incredible theories. We have a good idea of how our universe began, but not a solid one, as new discoveries challenge our theories constantly. We also have no idea whether this universe is the only one that has ever existed, either alongside our own or before it. But we could begin to answer these questions by using the power of 100 billion stars, by focusing large amounts of energy into one place, either with the goal of creating artificial black holes or even new universes through the generation of another Big Bang. If we last long enough to survive the dying of the final stars, forecasted some several trillion years from now, we may be able to use the energy of our galaxy, either stored in batteries or harvested from stars whose lifetimes have been artificially and significantly elongated, to create a new and energetic universe as humanity's ultimate escaping of fate. A race of intelligent beings with the experience and growth of an entire universe's worth of time, given a new one to shepherd and inhabit. It is truly difficult to comprehend what our forms and desires will look like so far into the future, where we today would have more in common with bacterium than our own descendants. Who knows how our priorities, cultures, and biology will change given a billion years of progress. But one thing remains clear. With the power of an entire galaxy behind us, absolutely nothing, natural or otherwise, will be a threat to humanity ever again. Thank you all so much for watching.